Hello, my name is Novikov Oleg. I study at school number 409. And today I'd like to present you my scientific work on the topic development of sensor substrates based on melamine-barbiturate-silver supramolecular assemblies. If you ask me why we consider this topic relevant, I'll answer that over the recent years, microstructured gold, silver, and copper substrates have been of the great interest in the field of analyzing microorganisms, cells, catalysis, and also in surface-enhanced Raman spectroscopy. But the problem is that current platforms have got a number of disadvantages. It is surface degradation over time, resulting in poor signal quality and inability to reuse substrates. Coming up to the objective of our study, we see it obtaining sensor substrates based on supramolecular assemblies of melamine barbiturate with silver by means of self-assembly formation features at the interface. There are several tasks targeted. They are highlighted on the screen. Among them is literature review, examination using mathematical and microscopic research methods, and identifying prospects for creating such substrates. During the last decade, scientists create supramolecular sub-assembly organic structures that could be good platforms for integration new components, such as MBA structure from the first article. Integrating new component in such a structure, specialists got the substance with the new properties, such as semiconductivity or UV absorption. After that, new structures are examined using various microscopic methods. For example, atomic force microscopy as in the third work. In case of obtaining microstructured surface, mathematical research methods such as Voronoi entropy are of the great interest. And regularly dispersed metal nanoparticles that exhibit plasma resonance are of the great demand in producing surface-enhancing substances. In the first steps, melamine and barbituric acid were mixed together to form small crystals of MBA. After that, 10% ammonia solution and silver nitrate were added and crystals dissolved. Organometallic complex was formed, applied on quartz glass, dried, thermally treated, and after that studied by various methods. In this slide, we can see the melamine barbiturate silver film before calcination, figure A and B. In figure B, we notice periodical hexagonal film. After that, we calcinate our film and got micro and nano agglomerations that were unknown for us. At the next stage, it was important to identify the presence of silver in the samples. After the energy dispersive X-ray analysis, we understand that we've got an argentum in periodical hexagonal film, as well as in nanodots that we received after calcination. To check the accuracy of the results, X-ray diffraction method was also performed. It showed the presence of metal silver in the sample and also the small amounts of silver oxide. This was followed by atomic force microscopy study. The method was used to determine the shape of micro and nano agglomerations and their heights above the surface. Thus, we understand that our microagglomerations are of the shape of hemispheres and are approximately 200 nanometers high above the surface. At this stage, structures were studied by Voronoi entropy calculation. We used the combination of two software packages, MATLAB and ImageJ. In figure A, we can see the sample that was obtained at 600 to 800 degrees. And in figure C, we can see the sample that was obtained at 400 to 600 degrees. The value of Voronoi entropy for the samples that were obtained at different temperature represents the structure with conserved periodicity that was proven by the calculation of Voronoi entropy. Such structures could find its application in surface-enhanced Raman spectroscopy. The point is that for accurate analysis of substances in ultra-low concentrations requires the sample that would amplify the light and thus simplify the identification. Therefore, we decided to do our own analysis of CERS effect. Rhodamine 6G was used as an analyte. The sample that was obtained at lower temperatures represents the structure that have intensity approximately 75% higher than at higher temperature. This effect could be explained by the fact that metal nanoparticles of smaller size contribute more to the CERS effect because of high concentration of surface plasmons. Here you can see the story of success. Because these are my first steps as a beginner in infochemistry field. However, lots has been done in terms of analysis, experiments, and observations. Lots of scientists are involved in this work, and I really appreciate it. So, back to results. During the work, periodical hexagonal film was obtained, microstructured surface was obtained, mathematical and microscopic research methods were performed. The possibility of obtaining microagglomerations by heat treatment of organometallic complex was performed. And as a result of the study, the sample that could find its application in surface-enhanced Raman spectroscopy was obtained. Thank you for your attention. I'm glad to answer your questions.
So, I have actually many questions. Let's start from the very simple one. In your papers, you stated that you used 10⁻⁵ molar concentration of rhodamine. That is pretty high for Raman, and also you performed some maps. So there are two questions. The first is what is about enhancing coefficient or enhancing factor, and the second one is about locality of let's say spatial locality or spatial resolution of Raman microscopy.
Thank you for a question. Talking about the intensity factor, nowadays we can perform these kind of results because we compare our samples together, and nowadays we didn't measure the size effect factor. And it is the fact that we like to do in future because this kind of methods requires more experiments, and we'd like to do it. And talking about the dots that we may create our graph, we choose the dots with the highest intensity of each sample, and after that create these graphs.
Okay, what about resolution, let's say spatial resolution or locality of the Raman?
You're talking about the plasma resonance?
No, I'm talking about the maps. So you have maps, and then you have each pixel is like 1.5 micron.
Yes.
Like, is it reasonable or not? What is the smallest spot you can get with optical microscopy?
Well, it's a really interesting question, but nowadays I can't answer it because it is too complicated, and I'm deep in research and like to read about it. Thank you.
Thank you very much for your report. I would like also to ask some questions. First of all, I would like to know what is the mechanism of surface-enhanced Raman intensity. Could you explain?
Okay, thank you for your question. In surface-enhanced Raman spectroscopy, we've got the laser that goes into the substrate, and after that, it interacts with the molecule in this area. Also, it is important to have the special substrate to get the good graph to identify the molecule on the surface, and after the integration with the molecule on the surface, light reflects and then go to the matrix, and thus we can understand the way our what molecular is, what kind of molecule.
How do you think, could you use any metal for these, for making such substrate, or just only several special metals?
Yes, we can use only special short kind of metals in such methods. For example, gold, copper, and silver, because they have got special optical properties, and thus not every metal could compare to our targets.
Which optical properties?
For example, silver that are really close to, or metal nanoparticles of gold, silver, and copper, which are really close to each other, can exhibit plasmon resonance, and thus we can simply identify the presence of substance on the surface.
What about other metals? If they will be just the same size, how do you think? Will they have some plasmonic resonance or not?
To my mind, no.
What is plasmonic resonance?
Plasmonic resonance is an enhancement of the light that we can get in case of metal nanoparticles that are really close to each other. The light goes to each area, and after that enhance and goes to the matrix, and thus we can get the better graph.
Did you suggest or did you prove the formation of the complex of melamine, barbituric acid, and argentum? So the complex formation, did you suggest it or did you prove it, and how?
Thank you for a question. We did some DFT analysis, and this way we understand that we could get this kind of complex. Also, we got the works of our colleagues that got the structure of MBA, and also the work where people get the structure with cyanuric acid, melamine, and argentum. Thus, we could make our hypothesis, and thus we after making an DFT analysis, we understand that we could get this kind of complex.
Yeah, I agree.
Thank
DFT
you,
is
thank you.
calculations, it's not analysis. Okay, I have very short, very simple question. Do you think CERS is possible on separate single particles, nanoparticles?
Can you repeat, paraphrase it maybe?
Do you think that Raman, in your case, CERS, so enhanced Raman, is possible on single nanoparticles?
CERS effect? No. We have to have the special substrates where metal nanoparticles are really close to each other. And
in your case, is it single nanoparticles or not?
In our case, these nanoparticles are on the surface and got the conserved periodicity. Such factors could help us with.
Okay, the question is, do you think they're single or not?
Single or not what?
I mean, you have nanoparticles on the surface. Do you think they're single or not?
Particles are single, they are not linked to each other.
So there is no CERS?
No, there is a CERS because they are really, there is a really short distance between them. So we can use them as a CERS substrates.